Hello, my name is Javier Rodriguez, and welcome to our lab number 2 of Physics 2211, the motion of a falling object. Now, the objectives and purpose of this experiment is to observe and analyze the motion of an everyday object that's falling from an intermediate height. Then model this data using VPython. By utilizing Newton's second law to predict the motion of the object over very small time intervals, we can determine the position of the object and the actual motion that it will produce. Here we have Newton's second law and the position formula derived directly from it. Finally, we want to analyze the objects in two situations, one where both gravity and drag forces affect the object, and one where only gravity affects the object. It is also important to determine if the object will ever reach terminal velocity. Now, as I just stated, we made two models for this experiment, one that accounts for drag force and one that does not. When the position data obtained from Tracker was compared to both of these models, the model which accounted for both gravity and drag forces was much closer to the actual data produced rather than the one that only accounted for gravity forces. Now, here are the two forces affecting the object in real life. The drag force acts in the opposite direction of gravity and is calculated using the falling object's velocity. Here we can observe the formula for F drag, where negative b is the drag force constant. Here we have and we also have Earth's gravity, which is pushing in the opposite direction of the drag force. It's pulling the object downwards towards the Earth. Now, here we have our data obtained from Tracker. A small paper ball was thrown from the top of this door to the bottom of the floor. The height of the door was actually calculated using a measuring stick and was found to be 2.06 meters. This is used as a calibration stick. Now, the axis had to be slightly tilted since the ball curved a little bit while it was falling. However, you can see that our graph is still a curve produced here. But towards the end, you can see that we have more of a straight line. This is when we reach terminal velocity. Now, also, you'll see that the object's velocity is speeding up towards the negative y direction. Here we have the initial part of our VPython code. Here we have the ball's mass, our initial positions, our time step, which is this means an infinite repeating series of decimals, and our gravity, which we know will always be 9.08, and our g hat, which is just for direction. Our b here is 0.01. However, when we don't account for drag force, b will always be equal to 0. Here we have the results produced from a model that does not account for gravity. As you can see here, we commented out the drag force formula. So we only have W, which is the force of gravity. Now, when only that is applied, you'll see that we only have one yellow arrow pointing in the downwards direction towards Earth, as gravity does, and we'll have a normal curve. However, once FD is uncommented and we have a total net force that is the gravity plus the force of drag, we will see that we'll have two arrows now. A gravity arrow pointing in the downwards direction and a drag force arrow pointing in the upwards direction. Also, the curve will be slightly different, and you can see that it gets straighter later. This means that it has reached terminal velocity. Here we have our final results. Now, as I mentioned, the model data with drag force, this line right here, is much closer to our actual observed data. This is due to the fact that in real life we have drag, while in the other model we don't account for drag, only gravity, which is an inaccurate depiction. Now, as you can observe, there are some discrepancies here. This may be because of imprecision when using Tracker, inaccurate measurements, or simply because of the small tilted axis. Finally, we can conclude that Earth's air creates a turbulent force opposite to the direction of gravity. This is why the model only accounts for the force of gravity, doesn't produce accurate results. And terminal velocity is obtained when gravity and the drag force are equal in magnitude. Now, a small what-if question. So, say the object is actually thrown downwards instead of being simply dropped. If this were to happen, we will notice that the terminal velocity will be reached much quicker. In other words, we'll have a straight line faster than if we simply drop the object. This is due to the fact that the object is now actually going faster and the drag forces affect it quicker than if it were simply dropped, where initially only the force of gravity is affecting it. Well, Thank you for listening. I hope you learned a little bit about physics today, and have a good afternoon.